Okay. So this is a very nice long review paper by a lot of authors. I think it's led by Pedro Di Nezio. I hope I'm getting it right. No, it's read by Aishu Hu. But anyway, as usual, I don't show author names. It's my convention. I show the DOI, so you can go and read the paper. I'm going to be supremely brief as usual. It has a lot of material, and as usual, it relies on all the published literature to put together the state of the art in terms of our understanding of the Atlantic meridional overturning. If you don't know what that is, you can follow up on my other podcasts. And the El Niño, which is the monstrous zonal mode of variation in the tropics with global teleconnections, and other tropical basins, which is of course Indian and Atlantic Oceans, because the El Niño happens in the Pacific, and the time scales are also very different. When you think about Atlantic meridional overturning, you typically think about low frequencies, decadal, multi-decadal, and it's in big news because there have been articles about whether it's going to collapse or not collapse, and whether it's slowing down or it's not detectable, lots of stories. But you will see that we know a lot of things. There are hints of a lot of things happening in terms of the interactions between El Nino, AMOC, Indian Ocean, Atlantic Ocean, and Indian Ocean, Atlantic Ocean interactions with the El Nino, and so on. And yet, in general, the sample size is very small, and you would want to answer a lot of the questions by using models, and we do try to do those, but we have to remember that the models have their own deficiencies. Even though they are amazing, given the energy at the top of the atmosphere, they can do all these things, El Nino, Indian Ocean dipole, Atlantic Nino, Atlantic meridional overturning, PDO, Atlantic multi-decadal variability, and so on and so forth. With all these caveats, we just run through few main points of the paper with incredibly long reference list as usual, because review articles tend to scour through the literature very carefully. Okay? Alright, with that, let's start reading the abstract. Tropical basin interactions and the climatic linkages between mid to high latitudes and the tropics are active research areas, which means we don't all have all the answers. These interactions include the influence of El Niño Southern Oscillation on the tropical Indian and Atlantic Oceans and the feedback from these basins onto ENSO. We have discussed this elsewhere already. The influence of the tropics on to the mid and high latitude climates and the feedback from higher latitudes on tropical variability. We have discussed some of this in the context of high latitude impacts on the monsoon, for example. This review summarizes the current understanding of these relationships and key underlying physical processes. Lots of very good details there, which I will mostly skip. Ocean's role, atmospheric role, mean circulation, zonal and meridional waves, and so on and so forth. In particular, we assessed the current knowledge of tropical variability and the interactions between the tropics and the extratropics, including ENSO variability and diversity. We have discussed this also. We'll see again what it means. The influence of ENSO on the tropical Atlantic and Indian Oceans, interactions among tropical basins on different time scales, variability in the Atlantic meridional overturning circulation, effect of tropical basins on the AMOC, Atlantic meridional overturning circulation, the relationship between AMOC and the Atlantic multi-decadal variability AMV, the influence of AMOC on ENSO, tropical variability, and the impact of other mid to high latitude processes on tropical variability. So when we talk about interbasin interactions, we are assuming that they have independent minds, and that is true, but we don't always know whether the ITCZ, which runs across and breaks into pieces based on the season and so on, is somehow a global conveyor of the signals, and whether this separation is artificial or whether that's real, because the Pacific and Indian Oceans are connected via the atmospheric bridge and the oceanic tunnel through the Indonesian through flow, whereas the connection from the Atlantic to other tropical oceans is only via the atmospheric bridge at short time scales. In the long time scales, of course, AMOC connects all of them and so on. Okay? So it's a long story. Although ENSO is the dominant mode of variability on interannual timescales, its characteristics are not stationary and can be influenced by processes from other tropical basins and mid to high latitudes. The strength and variations of these interactions among different tropical basins and latitudes can be modulated by changes in external forcing, whether of natural or anthropogenic origin, and may also be shaped by nonlinear interactions between different modes of internal variability. So quite complicated even without any anthropogenic forcing or orbital forcing, which are external forcings. The system has internal variabilities because of the internal nonlinearities and memories in the ocean and so on, and we know that from paleo data, for example. But now we are mixing anthropogenic forcing with internal variability, and there are some hotspots where internal variability is heavily modulated by anthropogenic variability, and AMOC is one of those debating points, and we'll address some of it in the ENSO context as well. And the Indian Ocean is warming fast, and it's being influenced by warming on land in the Middle East, so everything is connected to everything. But still, understanding these in a reductionist approach helps a little, but you will see that there are lots and lots of open questions still. Okay, jumping right ahead then, I take bits and pieces of the text based on my own reading as to what points I need to make, but you need to read the paper if you want all the details, right? So this is the end of the introduction here. Because the interactions between different tropical ocean basins, the Atlantic multidecadal variability or AMV, and the tropics, and the AMOC and AMV are all important for climate variation, this article reviews the current understanding of these relationships, the underlying physical processes, and their influence on climate change. We begin with a review of ENSO variability and diversity, focusing on changes in ENSO temporal evolution and spatial patterns, followed by a description of the mutual interactions among the tropical basins and an examination of the AMV-AMOC relationship and the interactions between the AMOC and the tropics, and a discussion of the broader influence of extratropics on tropical variability. So basically everything. There are articles focused just on ENSO variability and diversity, which means they are much more detailed than here, because this is part of a bigger paper. I think Antonetta Capotondi, for example, has led a nice paper on that, and she was trying to explain to me why I'm not always involved in those papers, but anyway, it was a fun discussion. Changes in ENSO characteristics over the past 50 to 60 years. I will just say in words that there is a lot of debate about how ENSO is responding to global warming, and we don't have a very solid answer, because that is important to say what ENSO will do into the future as we keep increasing emissions, especially with the scenarios and the CMIP6 projections out to 2100 and beyond. But still, people extract some signals of how ENSO has changed and will change in the future, etc. So skipping over all those details, which we have discussed a little bit elsewhere, in addition to greenhouse gas forcing, super El Niños may be induced by influences from the Indian and Atlantic Oceans when aligned correctly. Why am I reading this suddenly? Because it says how we are speculating based on what is observed. So we know greenhouse gas is increased and it's forcing everything, in especially the tropical Pacific, because the east is cooling less than the west, and this has some potential for positive feedbacks and so on. And El Niños, as I said, not enough samples at all to say anything specific, but yet we have the concept of super El Niños like 82, 83, 97, 98, 15, 16, 2015 and 16 and so on. And then there is the idea of whether they are internal variabilities as well, and how they are affected by Atlantic and Indian Oceans, and how the response of the Atlantic and Indian Oceans to anthropogenic forcing will affect these interactions. So it's a very complicated story, right? Super El Niños are more likely to occur if an early developing El Niño starting between March and June coincides with an Atlantic Niño in summer and a positive IOD in autumn. So this obviously opens another question whether Atlantic Niño in summer and positive IOD in autumn are independent of the Super El Niño, or if the Super El Niño itself is growing for some reason of internal positive feedbacks like Bjerknes feedback in the Pacific, and that's creating Atlantic and Indian Ocean responses. Because remember, El Niño peaks in December, January, February, and IOD peaks before in September, October, November. Atlantic Niño peaks even earlier in June, July, August. So how are these stacked up in terms of their interactions? This constellation is referred to as an Indo-Atlantic Booster. So some paper is there on that, you can follow up. The early onset endows Super El Niños with adequate strength in summer to excite wind-driven responses over the Indian and Atlantic Oceans, facilitating the Indo-Atlantic Booster mode. In return, the Indo-Atlantic Booster IAB enhances zonal winds over the Pacific Ocean, augmenting Super El Niños via Bjerknes feedback. I have discussed these elsewhere. If you don't know, please follow up. Basically, you have westerly wind bursts on the western Pacific that start early on in these Super El Niños, and then they become so-called multiplicative noise because they keep pushing the warm front eastward and then getting stronger and larger in fetch and have a strong ocean atmosphere feedback, which is the Bjerknes feedback, which we have discussed elsewhere as well. Okay. In return, the IAB enhances zonal winds over the Pacific Ocean, augmenting Super El Niños via Bjerknes feedback, SST variability over the northern tropical Atlantic and the subtropical northeast Pacific, referred to as the North Pacific meridional mode, during the early boreal spring has been suggested to trigger ENSO events. So we don't know whether the westerly wind bursts in the tropical Pacific are part of the North Pacific meridional mode. We have discussed this elsewhere as well, right? The joint impacts of both northwestern hemispheric precursors are projected to increase with global warming and can increase the frequency of Super El Niño events. This part is, I would say, speculative based on models that are imperfect. Let's say models don't do El Niño frequency, duration, and intensity as well as seen in nature, especially in terms of the El Niño diversity, let's say, and so on. So there are lots of reasons to worry about such projections, okay? Especially because models haven't explained very well what has already happened with El Niños in the 20th century or even the Holocene and so on. So the first figure coming up here is looking at ENSO indices and patterns. An ENSO index defined as the area weighted average of Niño 3.4, which I won't go into because we've discussed it elsewhere. B is an ENSO index defined as the first principal component of the EOF empirical orthogonal function analysis, because that's a dominant mode even if you take a global EOF, but especially when you take the Pacific EOF, as you see here. This is the principal component 1. This is just the raw anomaly Niño 3.4, and this is called the Eastern Pacific El Niño because it's centered on the coast and the Eastern Central Pacific, whereas this is called Central Pacific El Niño or Dateline El Niño because the warming is more focused here, and sometimes you also have cooler SST anomalies on this side even as this becomes warm here. And this is supposed to be different in terms of its teleconnections to the monsoon or the southern Atlantic, as we will see later on. So here you see the El Niños in reddish and La Niñas in bluish. There are some basic characteristics that we have discussed elsewhere. El Niños tend to be multi-year more often than La Niñas tend to be multi-year events, and there are reasons for that that are discussed in many papers. And the El Niños do not tend to be so often multi-year events, but you can see some here, maybe here, and so on. But these are the so-called super El Niños, big, huge El Niños. So this is Niño 3.4. This is when you focus just on Eastern Pacific El Niños, and you can see the amplitudes change here. This is because they are normalized to a different baseline. CP El Niños tend to be much weaker, obviously, because the warming around the dateline is not as strong as the East Pacific warming, and this is just the PC1. With the EOF analysis, you don't tend to separate the EPCP El Niños because it gives you this pattern, but on the other hand, the second mode may be looking like this, and there is also arguments about whether El Niño itself is changing in a way that typically this El Niño or this El Niño, even this El Niño, bring a cold horseshoe type SST anomalies here, and the cooling also extends into the maritime continent and the Indian Ocean, which by some people call as Indo-Pacific tripole, which tells you that maybe they are not independent and so on. But nonetheless, now more often you are getting a summer pattern where the entire tropical Pacific is warm instead of this cold SST anomaly pattern here, which can have implications for rainfall anomalies over here and so on. Okay, that's a global warming response. Well, it is because the warming over here is much faster, stronger than here. So there are implications of that as well that we have discussed elsewhere. So longitude time sections of composite SSTs and surface wind anomalies along the equator averaged over 3 south, 3 north, and this is going over the Indo-Pacific sector here, actually all the way into the Atlantic as well. So Indian, Pacific and Atlantic sectors with land in the middle, maritime continent here, and so on. So 1 year event of El Niño, so date goes this way, March 0, so El Niño year. You can see some westerly wind bursts picking up, and they get stronger as the El Niño grows into DJF and begins to decay in the spring of the following year. So year 1 here, March 1, June 1, and so on. Typically, after the El Niño has decayed, it transitions into a La Niña, but there are now studies talking about how the winter state of El Niño transitions into the summer state based on the teleconnections from the southern Pacific, another mode called the ENSO transition mode. A 2-year event typically looks like this. These are composites, so you have to be careful because each event tends to be very different. So you have Indian Ocean anomalies here, changing signs. So if you think about subsidence and cooling here, you have some pattern of subsidence and easterly wind anomalies on the Indian Ocean side, whereas it transitions to back to westerlies and easterlies over here because the cooling is typically associated with easterly wind anomalies, whereas in this event you again have westerly wind bursts growing, the amplitude seems to weaken and then picks back up, whereas the wind anomalies on this side remain. Initially they are different, but they remain easterlies through the second year of this event as well. So you have the cool anomalies here. So just remember these are composites, so I wouldn't imagine this is how every 2-year event evolves or even every 1-year event evolves, because it also depends on the strength of the El Niño and so on and so forth. This is the same thing for La Niña. So you have 1 year and 2 year events of La Niña. Obviously you have easterly wind bursts, convergence into this region, more rainfall, and then transition to maybe a weak La Niña, but not always. Again, composites can give you pictures of dominant El Niños making up the composite rather than all the El Niños and so on. And if you have a 2-year La Niña, then you can see here much stronger convergence and cooling here, stronger cooling here, and this seems to decay but then comes back. Okay, what do you learn from those? Not much, because we don't exactly have an answer as to exactly why those happen. Okay, so did I miss anything here? La 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 la. Yeah, okay. So shifting influence of ENSO on tropical basins and reciprocal effects of the tropical Atlantic and Indian Oceans. This is a long section. I'm going to cut it short and read just the front material and bits and pieces. As discussed, the ENSO characteristics have evolved in recent decades in terms of both spatial patterns and temporal evolution. These changes can modify the influence of the ENSO on other tropical ocean basins and in turn alter the feedback mechanisms from these basins back to ENSO. Right, so there is always a phase lag and then feedback, right? So ENSO begins to grow, influences the Indian Atlantic Oceans, and then Indian and Atlantic Oceans can in turn influence ENSO. There are lots of papers on this, but still you don't get a complete comprehensive picture because we don't have one. In this section, we review how ENSO impacts the tropical Atlantic and Indian Oceans and how these basins in turn influence ENSO dynamics. In addition, the influence of decadal modes of variability on the tropical basin interactions is reviewed as well. I'm going to skip many details and jump ahead to another paragraph which says, an enduring conundrum has been the fact that the strong 1982-83 and 97-98 El Niño events were followed by equatorial Atlantic SST anomalies of the opposite sign, so cooler, and Indian Ocean had IODs during those years. So in some ways the impact on monsoon was negated, impact of ENSO on monsoon, but remember ENSO monsoon correlation is only about 0.6 or so, so many events are not explained by many excess and deficit years of monsoon are not explained by ENSO, and we don't know how strongly monsoon itself can influence ENSO. Okay, there are ideas, but not seen every time. Kido et al. Used linear inverse models to demonstrate the role of initial SST conditions in the tropical Atlantic, indicating that intrinsic equatorial Atlantic variability cannot be neglected when explaining disparate responses of Atlantic and Pacific, especially different responses in the Atlantic to El Niños. Okay, so these inverse models basically take observed conditions and go back and say this happened because of this, so that's very important. It's kind of a AX equal B kind of problem that has a lot of value in using observations to explain processes. The tropical South Atlantic, jumping ahead again, the tropical South Atlantic appears to be more strongly influenced by CP than EP ENSO events. A CP El Nino event can trigger the second mode of the Pacific South American Rossby wave train, which we'll see in a minute, which leads to a weakening and northward shift of the South Atlantic subtropical high and a negative South Atlantic subtropical SST dipole. Many technical terms there, but please follow up with these references. You can see that already we are here at reference 146. The weakening of the subtropical high also reduces the strength of the winds along the southwest African coast, leading to favorable conditions for the development of Benguela Niños, which is the warming around Angola-Benguela Dome, which is strongly connected to the tropical Atlantic because the waves can travel very rapidly. Atlantic is a very small basin compared to the Pacific, similar to the Indian Ocean, so waves can cross very quickly, and there are additional details of how the ITCZ behaves over the tropical Atlantic as opposed to the Indian and Pacific Oceans. Okay, so there are other modes of variability called the Ningalu Niña. So there is a group in Japan which keeps giving lots of names to lots of things, but nonetheless, let's see if there is a figure that we should look at first. Maybe we should here. This podcast may be already getting a bit long, so I will stop because we can't finish this in one podcast for sure. So let's look at this figure and then come back to the next podcast. Okay, so this is a nice schematic of the interactions. So here we have a schematic showing various pathways of tropical basin interactions at interannual time scales in yellow arrows, overlaid on SST anomalies in red and blue shading. So there are different contour levels in panel A compared to other two, and orography, so green and brown shading because mountains make a difference. Magenta arrows indicate the influences of turbulent and radiative heat fluxes, so latent and sensible versus radiative fluxes. Individual panels show SST anomalies for DJF 9798, peak of that El Nino to illustrate the remote influences of El Nino events. In B, SST anomalies of May, June, July 1996 to illustrate the remote influence of Atlantic Niños and positive northern tropical Atlantic events. That's a little meridional mode in the Atlantic. And C is the SST anomalies in March, April, May 2016 to illustrate the remote influences of the positive Indian Ocean basin warming, which you can see here. So let's look at each one. DJF 9798, peak of that very strong El Nino, maybe the strongest of the 20th century. So you have obviously anomalous Walker cell. You have rising motion here and sinking motion here and divergence here and convergence here, obviously lots of rainfall and so on, and you have downward heat flux and warming. So remember, DJF 9798 had a very strong cooling here and warming on that side. So whether that cooling is independent of this cooling here, whether it's a really Indo-Pacific tripole mode, or whether there is local Bjerknes feedback here, those debates keep going on. But nonetheless, these teleconnections are or these mutual influences are very important. And on this side you have weaker trades happening here, so you have a bit of warming, so you have the other part of the local Walker cell here, and you have some influences going into the extratropics as well. So downward heat flux and warming here, and easterly winds and upwelling with cooling on this side. So you have a slight dipole feature here as well, even though this gets a lot of attention. We have Atlantic Niño and Atlantic Niña that also have influence in this whole game, or part of the whole game. Okay, so look at the scale here and look at the scale here, very different. So so this is going from about -3 to +3. This is only going from -1.5 to 1.5. Okay, because this is May, June, July when nothing is at its peak. So SST anomalies for 1996, which was a La Nina before the big El Nino of 97-98, and you can see very different pattern here. Basically, most of the basin is not having this strong anomaly in SSTs. So here you have easterly winds, upwelling and cooling. So that's got a sinking here and divergence here, and you have a strong Atlantic Niño type signal, and the Benguela Niño happens around here. And as I said, these are not necessarily always completely independent because of the wave connections, etc. So you have rising motion here and from the North Tropical Atlantic as well as the Equatorial Atlantic, and influencing the subsidence over here. So it gives you a sense of how complicated the interactions are, and we are just taking a particular time slice and saying this is how it worked, but it's a continuous evaluation, so continuous evolution, so you have to be careful nonetheless, because the easterly wind anomalies here may be related to the monsoon, pre-monsoon activities over here. March, April, May of 2016, which was the 2015-16 was a strong El Nino. MAM 2016 is the decaying phase of that El Nino, but it has strong Central Pacific El Nino type feature here, even though El Nino peaks in DJF. This is like a transition. So here you have rising motion here with the warm Indian Ocean basin mode, and that is influencing subsidence over here, clear skies, divergence and warming. So should this be driving this, or is this driving this? Obviously this is implying Indian Ocean is influencing the Pacific, at least at this time. So you have easterly winds, upwelling and cooling happening on this side, and you have the decaying part of the El Nino. There are a lot of details here because MAM, the sun is just crossed over into the northern hemisphere. ITCZ is trying to do its thing with the motion of the sun, and the ocean atmosphere interactions do their thing, and then you have a recovery from the El Nino, which means the recharge phase. So Atlantic here seems fairly calm for this period. But if you look at the evolution from let's say DJF of 2015 into MAM of 2016, you may get a slightly different picture, because when you take time slices even averaged over a season, you can always be looking at specific instances. Is this a typology that always happens in MAM of a big event? Of course not. So each event tends to be different, and yet we try to learn as much as possible in terms of the interactions. So we are looking at El Nino impact on the other basins, and we are looking at other basins impacts on El Nino. That's the main idea. Okay, so let's leave this here, because where was I? Yeah, so we didn't read this yet, so we read this, and then we jump to this figure. Yeah, we just read this one, so we will come back and start here, or maybe let me just read it. The influence of ENSO on the tropical Atlantic on a decadal time scale. So what we saw here is interannual time scale. There is also a decadal time scale. The influence of ENSO on the tropical Atlantic may be subject to modulation by interdecadal variability, such as AMV and long-term changes in radiative forcing. There's a lot of debate about whether AMV is just externally forced by greenhouse gases, whether the ocean is involved at all, or if it's just atmospheric internal variability and so on. But atmosphere doesn't have a memory, so you need, when you have multi-decadal variability, memory has to come from the ocean. The question is how, right? So if it's anthropogenic forcing, then greenhouse gas forcing can give you the atmospheric impact at decadal time scales, right? So long-term changes in radiative forcing may be possible. Studies suggest that the Pacific influence on the equatorial Atlantic is stronger during the negative phases of the AMV, such as the period of 1970 to 2000. So that's a multi-decadal period, whereas the North Atlantic Oscillation also has been important impact on the North Tropical Atlantic. Chateau et al. Indicated that CP ENSO had a weaker influence on the NTA than EP ENSO. So many papers, many ideas. This paper also doesn't manage to synthesize all of it together into a comprehensive picture, because we don't have a comprehensive picture, as we said, right? With the increase in CP ENSO frequency in recent decades, this would point to a weakening of the ENSO influence on NTA. Okay, there you go. CP ENSOs have a weaker influence on the northern tropical Atlantic. Northern tropical Atlantic has come up before. Basically, when the ITCZ moves here, you can have stronger trades and cooling here, weaker trades and warming here, which is called the meridional mode, and NTA is a big part of that, so it's asymmetric. So we should also remember that the La Nina impacts on the basins and impacts of the basins on La Ninas are not symmetric to El Nino interactions. So that's something to remember as well. Okay, so let's come back and look at the influence of ENSO on the tropical Indian Ocean and Indian Ocean on interannual and decadal time scales briefly. And there are quite a bit more discussion left, so I may need 2 more podcasts, but that's okay. We are not in a hurry. So let's stop this one here and come back to you. It's almost 34 minutes, but that's okay.